So let's wrap up this last section. Make sure you've seen the part 1 of section 11.2 where I show you the techniques on your calculator, because that'll make my descriptions go much easier, as I assume you've already seen these as I pull up my calculator to do some of this work. But the final topic we're discussing is another hypothesis test. The name of it is called a chi-square test. That's how you spell it out. And the symbol is the letter chi from the Greek alphabet, squared test. And the whole point of a chi-square test, like any hypothesis test, which will still have a null and an alternative and a p-value, is to essentially answer this question: is there a relationship between two variables? So here's what the null and alternative will always look like for every chi-square test. In general, it will sound something like this: the two variables are independent. That's always the null. What does it mean for two variables to be independent? Another way to think of what that means is that they have no relationship. The alternative is the two variables are dependent. In other words, they have a relationship. So keep that in mind as we work through two examples together, what the chi-square test is ultimately looking for. The other thing that is unique about a chi-square test, you know you're going to be doing one, is that the data we're given always shows up in a two-way table or a contingency table. So I've made up some numbers in a very simple table here, and you can see based on gender and answer, you could belong to one of four answers. So one thing that's kind of nice to do is you can complete the outside totals. You may be asked to do that in your homework. Pretty friendly. Looks like there were 50 males that were part of the survey, 100 females. 45 people said yes, 105 people said no, for a grand total of 150 people in the survey. This is what we'll call our observed data. So keep that in mind. This is what really happened of those four cells. Now, the question we want to know, is there a relationship between your gender and your answer? So one way we could start thinking about this is you could ask, well, what proportion of males said yes? If you ask this table of all the males, and I could use a little p hat for M, what proportion said yes? Looks like 20 out of 50, which is 40%. What proportion of the females said yes? 25 out of 100, which is 25%. So just with just observing some data, it looks like 40% of males say yes, 25% of females say yes. The question, does it look like the two variables, your gender and your answer, is there some relationship between those two variables? And on the surface, it looks like the answer would come out yes. It seems like males say yes a lot more often than females say yes as it comes to proportions. But with anything, that's always true as doing a hypothesis test. The data always supports the alternative. It looks like there's a relationship, but what we don't know is this evidence strong enough or not. And we're going to do a test at the alpha level of 5% and figure this out. So here's what happens next. As we learned in the first video, we're going to put this data in our calculator and see what all of this means. So I head to my matrix menu. Again, second, go find your matrix button. I head over to edit and I choose matrix A every time. This is a 2 by 2 matrix, number of rows, number of columns, not including the outside totals. So 2 by 2. And here comes my observed data, not including the outside totals. It's 20, 30, 25, 75. So we've just put the observed data in matrix A. So I go back to my home screen, second quit. I then head to my chi-square test, which is stat, tests, letter C. Chi-square test, I choose that. Notice there's another matrix called B, which is my expected. We're going to talk about that in a moment. We can skip right past it and move down to calculate and see what this tells me. In previous situations, we either had a test statistic called a z-score or a t-score. We now have a test statistic called a chi-square, and that's this top number. But what's going to help us make our final decision, like always, is my p-value, 0.0587. And we can already make the decision, because this p-value is greater than 0.05, we are going to fail to reject the null. But before I do that, I want us to look at another matrix. Head back to your matrix menu, second matrix, edit, and this time choose matrix B. As you saw in the first video, these are numbers you did not enter. These are not the same numbers we were given. These are what we call the expected values. So let me make a little room over here, and let me make a quick table and show you something. If I put my male, female, yes, no, and I put my expected numbers inside here, I've got 15, 35, 30, 70. My outside totals didn't change, as you'll see. 45 people still said yes, 105 said no. There's still 50 males, and there's still 100 females. But notice something interesting. On the expected table, ask the question we did up here. What proportion of males said yes on the expected table is 15 out of 50, or 30%? What proportion of females said yes? 30 out of 100, or 30%. The expected table is the same data rearranged so that it shows no difference between the two genders, which shows there's no relationship between your gender and how you answer this question. In other words, whether you're male or female, you would answer this question, 30% of all people say yes to this question, regardless of gender. And that's what we compare the observed with the expected. The expected is like the perfect version of the null. There's no relationship between gender and answer. So let's pull it all together then. If you remember on my screen, here's the final thing that really matters. There's a chi-square. I can jot that down. My test statistic, 3.57. But it's the p-value that gives me the power to make a conclusion. So 0.588. And here comes our familiar decision. First is, since my p-value is greater than alpha, we fail to reject the null. So what's my conclusion? Is we have weak evidence for the alternative. So it's possible there is no relationship, and I'll just say between gender and answer, or in other words, gender and how you answer the question are independent of each other. All right, let's take a look at a second example. I pulled this one straight from your online homework, so you may find you'll see something familiar when you get to this. But here's what we've got. There is a data set of restaurants, and restaurants are broken down by two variables. The size of the restaurant, does it seat 100 or fewer people, or does it seat 100 or more people? The other variable is, how's the restaurant rated? Excellent, fair, poor. So we've got a large sample of observed data. I'm going to skip filling in those outside totals. That's not that important right now. What is important? Let's set up my null and alternative. Let's call out my two variables, restaurant size and the restaurant's rating. So I'm going to state my two variables this time. Size and rating are independent. Always independent at the null. My alternative, size and rating are dependent. Okay, well, there's an expected table you'll probably have to fill in. Let me head to my machine and second matrix edit, number 1. This is a 2 by 3, and here comes my observed data. Once I put it in matrix A, I head back to my home screen, head over to stat, test, up to chi-square test, head straight to calculate, and I've got my final screen. But before I get there, you're going to be asked to fill in the expected values. And you get that by heading back to the matrix, head over to edit, and choose matrix B. And there the expected numbers are sitting there. You'll be asked to fill in maybe to 2 decimal places, so if I were to do that, for instance, here's the first one my calculator is telling me is 170.98. Head over to the next, 234.70, and you get the idea. But let's go ahead and make a conclusion on this test. Back to my home screen, my test statistic, chi-square, 16.57. My p-value, and this is a good example to remember, my p-value is not 2.5. This e to the negative 4 says move this decimal 4 positions to the left, and my p-value is actually 0.00025. If we were to call that to the 4th decimal place, I might call that 0.0003. But let's leave it at that. Let's say my alpha level is 5%. So my decision this time is, since 0.00025 is less than 5%, my decision is to reject the null. My conclusion, we have strong evidence that restaurant size and restaurant rating are dependent, meaning there is a relationship between the size of a restaurant and how it gets rated by its customers.